invertible phases.
All right. Thank you very much for the invitation. I've really been learning a lot the past week and looking forward to this week as well. So I'd like to talk about invertible phases and soft anomalies. And here are a couple of references, mainly for the first one or two lectures. Can people hear me with the mask, or is it okay? Okay, well, let me know if not. And please ask questions during the program. Okay, so let me start with some motivation. So, in much of these lectures, we'll be talking about gap phases, right? So, we have a system on some closed manifold, and we imagine that as we take the system size to infinity, the gap goes to some constant finite value. There can be ground state can have some finite degeneracy, but there is a gap to the rest of the spectrum. So we are studying these gap phases. And you might ask why. One answer is that they exist in nature. So we have quantum Hall effect, we have topological insulators, we have various kinds of spin liquids, so that's one reason. The other reason is that they are a lot simpler. I mean, the gap protects you. Many of you study conformal field theories, gapless systems, so those are a lot harder. And the third reason is that they provide a window into gapless phases. In which way? Well, oftentimes these gap phases support gapless degrees of freedom on their boundaries, and in fact that will be a major topic of these lectures. The other way that they provide a window into gapless matter is if, say, you have two different topological phases, two different gap phases, and you can imagine a phase transition between them. So that's some kind of exotic phase transition that, and we are in general interested in understanding whether these phase transitions can be continuous. All right. Now, in these lectures, I will mostly focus on a subset of all gap phases known as invertible phases. So invertible phases.
Is it appropriate to ask what is a phase?
Very good. So we have some action with some number of parameters. And a phase is defined as an equivalent class of actions where the partition function remains smooth in the infinite volume limit as you tune the parameters.
But the parameter, so this is like in condensed matter setting where I have a cutoff, say a lattice theory. Is that what?
That's right. It can be both on the lattice and in the continuum, but perhaps a little bit more natural on the lattice. And you should be able to throw in trivial gap degrees of freedom, and then potentially bring down their gap. And other questions? All right. So what are invertible phases? Well, again, let's have in mind this kind of lattice system, and to define the notion of invertible phases, we need to define the notion of stacking two phases. So suppose we have two systems with Hilbert spaces VA and VB, and we just stack them.
Actually, can I ask a question to follow up following up on the previous one, I always thought of the notion of phase, and at least in field theory context, to be essentially the same thing as the notion of vacuum of a quantum field theory. But here it seems that you're referring to the quantum field theory itself rather than the choice of vacuum in the situation with general vacuum.
I think for gap theories, you might require, for gap theories it might be a little easier. You just require that to have two Hamiltonians, right? And you say that they belong to the same phase if you can go between them without closing the gap. For a gapless phase, right? The gap is already zero, so it's a little bit more subtle. So in this context, I think it's more natural to think about the partition function and just require that the partition function be analytic in the thermodynamic way.
So just to give an example, if I take the Ising model.
That's right.
So how many phases would you say there are
there? I think maybe more less. Well, just in the simplest Ising model in the phase diagram, right, there are two phases. There is two stable phases. There is the ordered and disordered phase.
And so the disordered phase counts as one phase, is rather the fact that there are two buckets.
That's right.
That's the terminology.
Well, with the symmetry, right? So you can ask, given, if you ask the Hamiltonian to preserve this Z2 symmetry of the Ising model, how many phases are there, and there are two phases. But I think a more natural question is ask, okay, I have systems, all Hamiltonians, say in 3 dimensions with Z2 symmetry. And you can ask either the Z2 symmetry to be preserved or not. You can also differentiate whether it's spontaneously broken or not spontaneously broken, and you can ask how many phases are there in that set.
It seems that the language of the Hamiltonian you're using kind of, you're hiding behind it some implicit assumption of locality and some infinite volume limit.
That's right.
So
we will assume locality.
Yeah, just purely in the field theoretic language, is the phase the same thing as some equivalence class of deformation of quantum field theories? I thought.
That's right.
Yeah.
That's right. But I don't think that's different from what
I'm just saying that describing the Hamiltonian language, there are a bunch of additional assumptions one in principle would have to state about what type of.
That's right. So maybe I'll state those assumptions. We assume a Hilbert space which is a tensor product, local tensor product, and we assume that Hamiltonians are local. Just in the simplest, we'll be operating in the simplest context. Right, and then, okay, I have Hamiltonian HA acting on this Hilbert space, I have Hamiltonian HB acting on this Hilbert space, and then I can just consider the stack system to be the tensor product of these two Hilbert spaces, and I have a Hamiltonian like this. Alright, so this is the stacking operation. If you wish, this is A plus B, the addition of two phases. And then there is a natural zero in this setup for this stacking operation, which has just a phase which is continuously connected to the tensor product state, where the ground state is continuously connected to the tensor product state. So these dots are supposed to represent sides of a lattice, and then the ground state is just a tensor product of some chosen state on each lattice side. And of course, I can write a Hamiltonian H naught that has this as its unique ground state. And then there is a natural notion of inverse.
So H0 is just the sum of terms that they go
to. On site, it's a projector on site I onto this state side. Right, and then there's a notion of an inverse. And this inverse, well, for a phase A, Hamiltonian HA, we say that minus A is an inverse if, after stacking them together and tuning some local couplings, I can deform the system into a product state, deform the ground state into a product state without closing the gap.
So the HA plus HP lives in the tensor product of the original A and B theories.
That's right.
And so the vacuum also lives in this tensor product.
That's right. So there is a little bit of stabilization, right? Which is we should be able to throw in this product state. Tensor all our systems with this product state, and that's allowed.
Sorry, about this H0. I thought what you said earlier was that H0 could be any Hamiltonian such that the ground state is of the form you wrote, that's factorized, and that there's a gap, right?
That's right.
So that's not what you wrote. You don't mean the projector. I mean...
It's a local projector. So this is a representative, right? So each phase is an equivalence class of Hamiltonians that are connected without closing the gap. And this is a particular representative of that. Is it okay?
But in principle, it's conceivable that there exists some Hamiltonian H for which this zero that you wrote is a ground state.
This is actually a...
That's one but I just would like to continue what she said. So we could, is it true that we could find some Hamiltonian H for which zero is a ground state, but which cannot be continuously connected to H0 without closing the gap? A gap Hamiltonian.
You want this to be a ground state of some Hamiltonian?
It's not that I want to understand how rigid your definition. Am I supposed to specify both 0 and H0, or some simple Hamiltonian like H0, or is it just enough to specify 0?
So if you have two, well, maybe I'm wrong, but I thought if you have two Hamiltonians with a gap, then this is the ground state. If you take the sum of these Hamiltonians with any coefficients, that's also going to be true that this is gapped, and I'll make it not. Sorry, make it that's not the case.
Let's see. Well, you can always rescale. I think what Peter said is right, but yeah, I think that's right.
What's right?
You can take linear interpolation.
You can take linear interpolation. Right, if that was gap, lambda 1 minus lambda. Well, wait. I think this will work.
But the excited states are not the same, right?
The excited states are not the same. Yeah, but
The gap still seems staging from the boundary.
let's see. No, this will not work.
What? Now it's even more mysterious.
No, it will not work because at point lambda equal 1, you you have a zero gap on one of the sectors. So you don't want that. Or at lambda equals 0.
No. Okay. Well,
Let's maybe postpone this
Okay.
this discussion.
Okay. So then it's important to specify both state and the Hamiltonian.
I don't think it's important, but I can't think of a reason off the top of my head.
Okay.
There's some results in 1D or some arguments that generically if you are given the ground state and you ask if there's a local Hamiltonian which realizes that ground state, then that Hamiltonian is unique. I think it's expected to be true generally, but there's some rigorous arguments in 1D.
Unique up to what?
I think just unique.
No, I don't think that's.
It's a paper of Renard and Chi, I think.
I think you can have different local Hamiltonians that possess even gaps that possess the same ground state. There might be some more assumptions that you are.
There might be some additional ones. I think it was just locality, but I can.
Well.
But I think this Hamiltonian that you just raised will work because it is gapped, and the way you can see this is you can take expectation value in any state that is orthogonal to 0.
It's gapped at which point? At lambda?
At all points.
No, at lambda equals 0, it's not gapped because on the
No, the Hamiltonians act on the same system.
Oh,
Yeah,
on the same
only
paper.
one, yeah. On one space.
Basically, in a combination, you can say, okay, what happens if the Hamiltonian is non-commute, but if you check, you take the expectation value in any state which is orthogonal to the ground state, which is common to both Hamiltonians, you can bound it from below, this expectation value, because expectation value of every Hamiltonian is bounded.
Mhm. Okay, so perhaps this is the argument.
Sorry, stupid question, but I just understand the question. I Invertible goes over A and B.
Say that again?
I runs over A and B.
Over the side, no, over the sides of the lattice.
What is I should the left? So and psi, what is psi?
Psi is some local wave function in the local Hilbert space. Okay, can we move on? Okay. So okay, so phase A is called an invertible phase if it possesses an inverse. Naturally, these invertible phases form an abelian group under the stacking operation. And it's important to realize that not all gap phases are invertible. So if you have a topological quantum field theory and with anion excitations, then it's not invertible. And the reason is the following.
Sorry, Max, just to confirm, so the tuning here is still keeping the tensor product structure? Or
That's right. We always keep the tensor product.
So we're not discussing lattice gauge theories or anything like that. That's more south.
We're not discussing lattice gauge theory without matter. So there's always the Hilbert space is always a tensor product space. So if you have an anion model, I'd say the ground state on say a torus will have some some protected degeneracy, and no matter what I stack this with, let's say this is phase A and this is the putative, well, let's say this is some other phase B, the ground state degeneracy is going to be the product of the ground state degeneracies of the two, and this is a protected degeneracy, so I cannot lift it without closing the bulk gap. So therefore, there is no way to connect this to a trivial product state, whether it's just a unique vacuum.
What about case of spontaneous symmetry breaking up those invertible, like the disorder space of the Eisenhower?
Under this definition, no. I think. Let me think for a second. Yeah, under this definition, no.
So the setting of this lattice, does it have to be a lattice? I mean,
It could be in the continuum.
What I meant is, does it have to tile a manifold as opposed to just some discrete metric space with, or even just with some topology assigned such that you have a notion of neighborhood?
I think we want a notion of locality. We want
That's what I'm saying. But locality can be much more general than just saying that this lattice tile a manifold.
It doesn't have to be a regular lattice, although the notion of thermodynamic limit, of L to infinity limit, might be tricky if you have some system with disorder.
Mm-hmm.
Yeah. All right.
So basically, it has nothing to do with any. You just said that if there is a system which has more than one vacuum on a torus, which has degeneracy in the torus, it is not invertible, period.
That's right. But protect. There can be accidental crossings, and we have to be a little bit careful about that. In the case of Z2 symmetry, that crossing of the two ground states, in case of spontaneous symmetry breaking, those states are protected, right? So, but if it's just accidental crossing, it's a little bit of matter of nomenclature. You can add a perturbation that will lift one of the ground states.
Well, even if it lifts one of the ground states, if we have a continuous perturbation, we will never be able to, by small perturbations, lift these states all the way to the gap.
Well, I was just saying, suppose you don't have any symmetry, right? And you start with a system that accidentally has some level crossing. Or start with the Ising model in a spontaneously broken phase with a twofold degenerate ground state, and now say we don't actually care about the Z2 symmetry, then you can lift one of the ground states and go to this situation. Now, do you say that these are in the same phase?
I thought according to the definition they were not. Because when you do this,
well, you can say that if the gap,
partition function,
the gap goes to 0. So,
So, are you talking about the torus?
it can be any manifold.
But on the torus there's no symmetry vacuum, you just mean a very small gap.
Well, in the thermodynamic limit, right? L to infinity. Right, so this becomes exponentially smaller
That's flat space.
in the volume. So when
Okay, but then it doesn't matter whether you're on the torus or
But-
we start from the sphere.
for spontaneous symmetry breaking, it does not, but for TQ of T's with annual excitations, it does.
just when you close the gap on the torus by turning on the Z2 breaking deformation, even in the easy model, partition function has a singularity at 0 magnetic field. So your definition of a phase was deformations which do not create. This singularity will be there even if
Correct.
this degeneracy was accidental.
Correct.
So it seems to me that even if this degeneracy is accidental, you still have to, if it's exact accidental degeneracy, you seem to be still forced to say that it's just a phase. Right? So
But I think the point is that you can either go through the singularity or you can go around it, and the fact that you can go around it means that it's in this
Right.
instance. So I don't think just because there's one path where there's a singularity in the partition function doesn't mean that there isn't another path where there's not. So
I think what Slava is asking whether the Hamiltonian that realizes the spontaneously broken Ising model, whether that's in the absence of symmetry a separate phase. And I think according to this definition it is.
There is no path around it. At first to the phase transition, the partition function is not going to. That's an essential singularity.
So, can we move on? So what about these invertible phases? Why are they interesting and what are some of their properties? Okay, so they have, first of all, they have a unique ground state on any spatial manifold, as we just discussed. They have no non-local excitations, no anion excitations, because the presence of those excitations would imply ground state degeneracy, say, on a torus. And I think what's most interesting about them is that they have protected anomalous edge states. We will see that actually the field theories that live on their boundaries carry Toft anomalies. And then we're interested in Toft anomalies because they allow us to constrain RG flows between theories. And finally, what turns out to be the case is that these invertible phases have partition functions on closed manifolds, which are just pure phases. Of course, if we are dealing with these lattice systems, we have to, it's quite non-trivial to put it on some sphere or in general some curved manifold. So there is a little bit of a step between this, and in general what we will, when we make statements like this, we will pass to some kind of continuum field theory limit, and I'll give one example shortly. And well, what we already started discussing is that while we started out with classes of Hamiltonians without any global symmetry, one can add symmetry into the game, just restrict to Hamiltonians that have a certain global symmetry, and all the definitions pass.
I was supposed to be amazed by this. So you wrote this as if something. What is going on here? Is this something that we should be saying wow, or what's going on?
Yes.
Well,
Is phi a real number? Is it an imaginary?
it's a real number.
Okay.
So it's a pure phase up to local counter terms.
But the
involving-
partition function of the Ising model is definitely not a pure phase. So there is some free energy there, which is
At what point? In the gap phase, it is a pure, well, it's actually, in the trivial phase, it's just one.
well,
Right,
we
and
have
the-
one. Let's take partition function of the Ising model as a function of the temperature, some non-trivial function of the temperature, both in the
Right,
in the
but
symmetry.
say fix the, well, say fix the temperature, right? And my claim is that on any manifold, it will be some, let's see how to write it. There will be some cosmological constant, and then there will be some term like this. So there are always kind of terms involving the geometry of the manifold, and all of these terms can be eliminated by local counters. So that's what I mean, that the partition function of the Ising model in the disordered phase on any manifold is equal to 1.
Up to this local ambiguity.
Up to this local ambiguity. And we will be interested in the non-trivial phases, will be those where using these local and counter terms, we cannot eliminate the thing.
So this phi of mu, which is e to the I phi, which now disappeared, where does it sit? It sits in these things, or it sits something else that's going to be
Plus,
eliminated?
plus
Right there, please.
I phi.
You're not supposed to write where all the cross is erased.
We will see an example shortly. Other questions?
So just to be sure, the statement, underlying statement is that there's a topological quantum field theory that describe these ground states,
That's
I mean, it's much more than just a partition function, right? It has to obey, this sort of single axioms of topological quantum field theory, and they're like some, gluing the manifolds together and so forth. Can I understand, to what extent was that proven based on the Hamiltonian description? Is this equivalence, is this just intuition, or is there some rigorous statement?
It's intuition. It's intuition. And in fact, we have to be a little bit careful. I'll give a kind of a lattice system that's not of this type, but which is invertible, but which is not of this type in a second.
Could you comment on? I mean, maybe you're doing it later, but why? How invertibility implies that? Is this intuitive?
It's. I actually cannot prove it. Actually, let's see.
But it's roughly the idea that if it's invertible, it's because it's the one that, phase times the complex conjugate is one.
Right, but why can't they just have a real part? Why can't the other partition function be just 1 over that one, whatever that one is? Why does it need to be a pure space?
No.
I mean, I guess what I was thinking is, okay, maybe this phase has to be a phase because then you need to have the other phase that leads to the tensor product, so you need to be able to cancel it. So the other partition function should be to the minus I phi.
It's clear that on a by our definition on a manifold which is a spatial manifold across a circle, the partition function has to be in fact 1. And if I put some, say, symmetry twist on a circle, then it has to be a phase. But why on an arbitrary d-dimensional manifold it's still a phase? That's a little bit more tricky. I don't think. Well, I can't think of a proof off the top of my head, and I'm not sure there is.
Okay, can you explain why in the first statement is triggered? Because I missed also the first statement. Why on this manifold it should be 1?
Just the fact that there is a single ground state.
Sure. Okay.
No, what is it?
It's giving Hamiltonian picture where you're thinking of M as the special manifold and S1 as the temporal circle, and then it's 1.
No, you said that invertible means we can find B such that if you put A plus B together, you get something like that.
Yes.
But A itself, it can have.
Right. We just said that there has to be no ground state degeneracy. Right? And having no ground state degeneracy means that the partition function up to local counter terms will be 1.
Meaning the large radius limit where only the ground state contributes.
That's right.
But this argument doesn't even allow a phase, so.
But because the manifold has this particular count form.
Where do local counter terms enter? You seem to be proving just that there are these local counter terms, and somehow you assume that they can cancel only. That there can be imaginary part which cannot be cancelled by local counter terms, but all the real part can necessarily be cancelled. So why can't there be also a real part which cannot be cancelled by local counter terms? There seem to be some simple argument here that I missed.
I think, I think having, you will run into trouble here. If you have, you will run into trouble with having no ground state degeneracy on an arbitrary spatial manifold.
Why can't I just cancel a real part with the cosmological constant?
No, Slava is asking whether it's possible to have a real part that cannot be cancelled with local.
That means if you're not allowed to have the cosmological constant.
No, we are allowed that maybe there are some more complicated ones that just depend on the global topology of the manifold.
But if I shift the cosmological constant, I can always cancel the real part.
Well, suppose it's something that's not geometric, that, I don't know, depends on...
Well, I thought you wanted some notion of locality, right?
Suppose you have...
No, but Cartesian
so maybe you have, like, in 4 dimensions, you have trace R of H R.
I think you're still
Well,
not
okay,
allowed to
this is
write the
local.
rest.
Sorry?
I think you're still not allowed to write the
Well, let's see.
Sorry, but
The parameter must be called.
Anyway, so let me suggest something. So this is good because clearly there is a little bit of different language which is used in our community in Europe. So this was useful. At the same time, we want to hear what you want to say. So why don't you go ahead and try to indoctrinate us according to your viewpoint?
Okay. Let's leave these questions for discussion after lunch.
I think it's not just an issue of language, it's an issue that there are certain simple arguments that you assume that they are simple or obvious things for you, which...
I don't think all of this, I don't think all of these arguments are simple, and I don't think all of these things are proven.
sorry, what? Just with respect to what Balt was saying. I mean, free theory in 2D or whatever, a CFT in 2D as a partition function R1 where box R it's local, so partition functions are not local in the curvature. Those terms you will not be able to cancel with this kind of counter terms, for instance. So there's definitely R terms which are not cancelled with by local counter terms. Then okay, Slava was asking more, like why not all of them, or but okay, examples of local theories that give non-local partition functions are everywhere.
So there is I should say that there is a paper by Dan Freed and Michael Hopkins that develops the theory of these invertible topological phases in arbitrary dimensions, and they actually define them as fully extended quantum field theory. So they define what the field theory assigns not only to the top partition function but to kind of all levels, and it's understood that this class of theories is consistent unitary field theories. But to kind of...
But I think they're just taking it as an axiom that it's a phase. I don't think they're proving it in any way, right? It's one part of their assumptions.
Well, at least it's a way to construct those field theories as fully extended field theories. All right. So let's discuss what are some examples of these invertible phases or invertible field theories. Maybe better to call them invertible field theories.
So as a matter of terminology, are you assuming that they have a symmetry and I have to preserve the symmetry, or not necessarily?
Say that again?
Are you assuming that there is a symmetry that must be preserved, or not necessarily?
Not that we can classify invertible field theories with symmetry or without symmetry. So equivariant or non-equivariant. So without symmetry, what are some invertible field theories in all dimensions? And, well, I can deal actually separately with phases that have Fermat degrees of freedom, so where the Hilbert space is graded, and that only have boson degrees of freedom. And in the Fermat case, here is the classification in low dimensions. So, in 1 plus 1 dimension, there is the Kitaev wire, which we will actually discuss next. In 2 plus 1 dimension,
So with no symmetry, there's nothing.
no, this is with no symmetry. Other than permanent.
So what is this group here?
G2.
I don't understand.
No.
It's the Billiard group.
This is the group of invertible phases. Remember we said that the abelian phases form a group under
Okay.
stacking. In 2 plus 1 dimensions, we have the P plus IP superconductor, which has a chiral Majorana edge mode. This one has just a single point like Majorana at the Majorana edge. And in 3 plus 1 dimensions, there is nothing.
So this is the complete classification.
This is believed to be the complete classification. In 1 plus 1D, it can be proven. For bosons,
Sorry, could you say again what is the in 2 plus 1? What is the alternative here? P plus 1?
P plus IP,
P plus
yeah.
IP?
So that's just a condensed matter language, but you should think of this as a bulk term that has the bulk partition function has a gravitational Chern-Simons response, and the edge has a chiral Majorana.
What
Okay.
about higher dimension?
We actually we know the classification in any dimension, and I'll talk a little bit more about it. But these are the dimensions that condensed matter physicists some of the
Are there no phases in higher dimension?
There are phases in high dimensions.
So something is special about 3 plus 1, that there are no phases.
Well, there are some phases. I think there are some dimensions where it happens that there are no non-trivial phases. I think in 4 plus 1 there are no phases for fermions, but for bosons there is something. For bosons,
So when you say fermions and bosons, what do you actually mean?
right? So local Hilbert space, whether it's purely spins or it can have fermions. In the field theory language, it's whether you are dealing with spin field theories or field theories that are can be defined on non-spin manifolds.
But there's no assumption these are free bosons or free fermions.
No,
right?
no. These are all interacting classifications. Well, for fermions, it actually makes sense to also classify non-interacting fermion models, and there the classification sometimes is different. Sometimes you get new phases when you add interactions, sometimes old phases, some of them collapse to the same thing. So for bosons up to 3 plus 1 dimensions, there is only one interesting phase without symmetry, which is the so-called E8 phase, which has a boundary with the chiral center of charge equals. And one comment that I wanted to make in response to one of the questions is that, strictly speaking, if you are dealing with lattice systems, this actually doesn't capture all. In general dimension, this doesn't actually capture all invertible phases. For instance, you can have a situation, you can have a phase which is a stack along the third direction of a bunch of these P plus IP superconductors with chiral Majorana modes on the edge.
And why is it not captured?
Well, it doesn't have Lorentz, emergent Lorentz invariance in the infrared.
But are you using an infinite stack or a finite stack?
Infinite. Yeah, so it's a 3 plus 1 dimensional system. So perhaps this is better thought of as classification of topological quantum field theories, but turns out that up to a few examples, at least in lower dimensions, this actually seems to capture all the phases on the lattice as well. In fact, these weird things seem to only appear starting with 3 plus 1 dimension.
That's somehow related by the Lorentz symmetries of an accidental symmetry.
That's right. Often emerges into low energy field theory, and in the topological field theories, it's even more natural for it to emerge in a gap system.
And what about the same thing if you put T-type wires one on top of the other, then again you seem to be producing something weird?
There you can gap it out, right? There, if you don't insist on translational symmetry along this direction, no one prohibits you from grouping them together and gapping them out. Here you cannot, right? Really, the fact that it's a Z2 here versus Z is what. Yeah. So let's see. So that was next thing I wanted to discuss is the explicit construction of this Kitaev wire. So let me maybe start with that and continue next time. So Kitaev. So I'll start with the lattice model for this, and then go to the continuum. So we are going to work with fermions in 1 plus 1 dimensions. So just imagine a chain of fermions labeled by site I. And it will often be convenient to write this in terms of Majorana degrees of freedom, where on each side I split my complex fermion into 2 Majoranas. And this square to 1. Alright, so I can redraw this picture in terms of these pairs of Majoranas, gamma 1, gamma 1 bar. And now, well, let's begin with an example of this trivial phase, local tensor product. And well, the ground state is one where on each side I just have zero fermions, no fermions. So I can draw this schematically as just pairing up these Maranas, gamma 1 bar, gamma 2 bar, and so forth. And this has a unique ground state, either either with periodic boundary conditions or with on a finite chain, and the gap is 2. Okay, so this is an example. This is a realization of the trivial ground state, tensor product state. Here is another Hamiltonian that will turn out to realize the non-trivial phase. So here I pair the Maranas like this. Yeah. Here's gamma and bar. If I write this in terms of the C's, it looks as follows. Regular plus 1 plus plus 1 delta CI plus Alright, so if I have a closed chain, right, and this gamma n bar is connected to gamma 1, and there is again a unique ground state on a circle. With the same gap. However, if I have an open chain, then the ground state is twofold degenerate. These two Maranas, gamma 1 and gamma n bar, put together can form a complex fermion that is either filled or empty. So there is a twofold degeneracy. On an open chain. Whereas on a closed chain, the ground state is unique. And, well, think about how to live this degeneracy. Well, there is no term that I can write down that will, local term that will that will remove the degeneracy. I essentially have to generate this operator. And if I have some local terms, I have to go to nth order in perturbation theory to connect this end to this end. And so the splitting will be exponential in system size if I have some weak perturbation. Now, I claim that this can be thought of as an example of an anomalous boundary. Right? Two Maranas form a Hilbert space with dimension 2. So if I want to formally assign Hilbert space dimension to each Majorana, that will be square root of 2. So this is kind of a Hilbert space that we cannot realize strictly in 0 dimension with ordinary fermion degrees of freedom. What does it mean to have a Hilbert space of dimension root 2?
Sorry, what is the square root of 2?
Sorry?
Where does that come from, the square root?
You have two boundaries with Hilbert space dimension 2, so if I wanted to formally assign. And now, the last comment is, these two degenerate ground states, what is the difference between them? And it turns out that they have different fermion parity. Overall fermion parity of the chain is different.
Sorry, just a basic question, but they are very entangled, right, the two endpoints? It will not make, no?
No. Well, let's say we just, no, right? So if I cut, there is only a single bond that they cut.
Okay, so you really can choose any value for
All right. Right, so fermion parity. Is the product of fermion parities on each side. And because we have the ground state is an eigenstate of these operators, I can rearrange and write this simply as on the ground state, on this twofold degenerate ground state, for an open chain, this just reduces to gamma 1, gamma n bar. So the two ground states have opposite fermion. All right. Now, so this is a separate phase. And is it invertible, right? Does it have an inverse? And it turns out that it's its own inverse. Say I stack two of these chains together. Either open or closed. Well, if I stack two open chains, then you can immediately see that I can gap the edge out by pairing these Majoranas. But let's say you ask, okay, two closed chains, can I connect now the stack of two closed chains to a product state? Can I connect to this one? Without closing the gap, and the answer turns out to be yes. What you do is you take any, say, of these, you take each of these combinations of four Majoranas, and you can show that you can continuously go to this configuration without closing the gap, and then from this you rotate again to this configuration. So that's a good exercise too.
Sorry, what is the intermediate configuration?
Just all the bonds are vertical. All right, so
Sorry, a stupid question. Is it 2 copies of H1 or?
2 copies of H1.
Okay.
That's right. So that's why this phase is its own inverse, and we have this, it generates a Z2 group. So can I maybe take another 10 minutes or so?
Yes. We have, the coffee break is not till 45.
All right, so let me. So we have this non-trivial phase in one dimension. We see that it's characterized by a ground state degeneracy on an open segment. But can I already diagnose it on a closed chain? It looks like on a closed chain there is nothing special about it. And we'll now see a signature already on a closed chain. And the signature is as follows.
Sorry, Max, to understand a bit how the game works, to do this exercise for the close, so we would add terms to the Hamiltonian with the tunable coefficient and break this bit so that it dominates, something like that, or?
That's right. So you start from terms like this, and then imagine that you add terms like this, and you tune from, you add a lambda here, you add a 1 minus lambda, and you can show that that the gap remains finite. In fact, I mean, all you really have to show is that these two configurations have the same Fermat parity, because any two states, it's a zero-dimensional Hilbert space. Any two states in a zero-dimensional Hilbert space, as long as they have the same Fermat parity, can be connected with it via some path. So that's really all you have to show.
And how do we know that there's never any critical point in the middle, any closure orbit? Like, I don't know, if I look at the Ising model Hamiltonian, and it's also like a local interaction, but at some point.
No, but here you're doing everything, you can think of it just as zero-dimensional system, right? It breaks up into zero-dimensional systems.
Right. Okay.
Just to be sure I understand, so can you use the Hamiltonian that link the first and the second?
Yes.
Ah,
When you, under the stacking operation, you are allowed to add terms that couple the two legs.
You need to, right? Otherwise.
Of course. Okay. So let's the bond signature. The idea is you take the chain and you thread flux pi for the Fermat parity through it. Okay, so if you took a triple chain, so here is one, these are the sides. Well, because the sides are decoupled, when you thread flux, nothing changes.
Can you say, in terms of formulas, what it means
To thread flux?
to thread flux?
Yes. So imagine you have some Hamiltonian, which is a sum of local terms. Suppose I want to put a flux defect across some cut here. In one dimension, it's just across a point. Then for any terms in the Hamiltonian that connect that go across this cut, I conjugate the left side, say, by the symmetry that I want to insert flux for. this is the way to do it on the lattice. So really I'm inserting a flux defect line. So for a system that's in the trivial phase, it does nothing.
But Max, I'm sorry, I have to insist. You said thread flux phi. Now you wrote some equation. Phi doesn't appear anywhere.
Okay,
You should just give an example of what this means.
So this is nomenclature. So
we
here
have a Hamiltonian written there, right? C is.
in this case, this is for general symmetry, and in my case, the symmetry is just fermion parity, and I'm using u equal -1.
So phi would be the infinitesimal generator size. So
If I had a u1 symmetry, then this would be a u1 transformation with flux with phase equal to phi.
We have a very explicit Hamiltonian.
Yes.
C digressive. Can you just write down what this means in terms of this Hamiltonian
Yes.
as an example?
So let's go to the non-trivial phase. Right? Just for the trivial phase, there is nothing. There are no terms connecting. If I make any cut, there are no terms that cross the cut. So there is nothing to do. But for the non-trivial phase, there is.
But the Hamiltonian still changes. So we are here two things. There is a Hamiltonian which changes, and then when you say there is nothing to do, Hamiltonian changes, right?
No, in this case, for the trivial phase, the Hamiltonian does not change. Because there are no terms in the Hamiltonian that connect any two sides.
I see. Okay.
So H naught just goes. Bar. So this is a closed chain. And let's say I want to insert a flux between site n and site 1, right on my closed chain. So I have this term connecting site n and site 1. The term is I gamma n bar gamma 1, and I conjugate now gamma n bar with fermion parity becomes minus I gamma n bar gamma 1. Right, so this is the only term in the Hamiltonian that changes under this flux insertion. So the ground state after the flux is inserted is still unique, but instead of having I gamma n bar gamma 1 equal to +1 or minus 1, instead of having it equal to -1, it's now equal to +1.
Is it correct to say that in the bosonic case, without any symmetry, you can't use such a trick to diagnose whether a phase is non-trivial?
Correct. But we will see that we should think of this really as putting the system on a non-trivial manifold. In this case, with some non-trivial spin structure. In the bosonic case, you just put it on a non-trivial manifold with some non-trivial topology. Okay. Interesting. Now, let's think about the total fermion parity of the ground state. remember for an open chain, we said that we had a twofold degenerate ground state with the two states distinguished by Fermat parity, and in fact, the Fermat parity was equal to I gamma n bar gamma 1 on the ground state. So if the eigenvalue of the ground, if the eigenvalue of I gamma n bar gamma 1 changes, that means that the Fermat parity of the ground state changes. So it means that minus 1 to the f on the ground state changes from plus 1 to minus 1 as we insert this, as we insert flux.
Is the insertion of the flux still breaking? I mean, it would look like it breaks some translational symmetry, right?
So here, first of all, we will not care about translational symmetry. Second, it looks like it breaks translational symmetry, but there is a combination of translational symmetry and gauge transformation, or really action of Fermat parity on the site that is preserved once we put the flux. So really, it's still
okay. It's still close. So this is not like replacing two boundaries with an interface. It's really just this is still a closed system.
That's right. That's right. You know, it's like you have a defect line, but this defect line is topological, so you can move it around. Okay, so what does this mean in terms of the partition function of the system? Let's think about the partition function on a torus. Okay, so if you have a unique ground state, in the large, in the low temperature limit, that's what we get for beta times gap much bigger than 1. And if we just tune the ground state energy to 0, then we just say this is equal to 1. Right? This is an example of that local counter term that we were talking about. Okay, so the partition function, we said that without flux or with flux, there is a unique ground state, so the partition function in both cases is equal to 1. But now, what about the following? What about this kind of modified partition function where we insert the Fermat parity operator? So as this limit, this will pick up the Fermat parity of the ground state. And therefore, this twisted partition function switches from minus 1 to plus 1, plus 1 to minus 1, as we insert flux.
You should try to conclude.
Yeah, I have like 1 more minute to go. So then, if I think about this as partition functions for fermions in a torus, then I can have periodic boundary conditions or antiperiodic boundary conditions along each torus direction, and I can make the following table. So let's say this is the spatial direction, and this is the temporal direction, and for the non-trivial chain, in 3 of the sectors, in the antiperiodic is Nevar-Schwarz, periodic is Ramon. In 3 of the sectors, the partition function is 1, but in the 4th sector, the Ramon-Ramon sector, the partition function is minus 1. So we can detect this non-trivial phase on a torus by looking at its response to different spin structures. And we will see that this is a general lesson for invertible phases. We can detect them already on closed manifolds, but by making the manifolds topologically non-trivial, and if there is symmetry involved, by inserting symmetry classes. So let me stop here. Continue next time.